Hi everyone. Good morning, good afternoon, and good evening to whichever part of the world you are in. A very warm welcome to each one of you for today's live session on Time Series 101. And for those unattended about Dphi, we are a data science community which we started with a vision to build data culture and democratize data science learning. And in our endeavor to constantly give back to the community, we regularly conduct boot camps, live sessions, and workshops from the industry experts. And also we conduct datathons and other events. And today's session on Time Series 101 is one such initiative. And our heartfelt gratitude and many thanks to Mr. Srivatsan for kindly agreeing to do this. And I'm confident most of you know about him, and most of you must have been following him on LinkedIn or on his YouTube channel. If not, please do follow him. And for those unattended, Srivatsan is a chief data scientist at Cognizant, and he's also founder of AI Engineering YouTube channel, where he frequently updates us with several tutorials related to data science, machine learning, data engineering, etc. And he's a big fan of everything that's related to data, and spent over a decade and a half in building data-driven products for leading financial institutions out there. And as you might, all of you are very much aware of his invaluable contributions to the community, and he continues to support many budding data scientists and data science enthusiasts through his tutorials and regular updates on LinkedIn. With that, once again, thank you very much, sir, for joining in with us today. And I'll let you take over the session from here on. Thanks.
Yes, sure. So good morning and good evening, everyone, depending on which location you're joining from. I think my introduction is already done, so I'm just going to get started. I'm not going to give one more round of introduction. So let's get started. This particular webinar is going to be about Time Series 101. So I'm going to talk about some of the basic concepts of time series. Now, when we talk about time series and other machine learning techniques, the process of insight is same, but the techniques and the statistical methods that we use to derive insights is completely different when we talk about time series. So I'm going to talk about those various concepts, various terminologies that comes in time series, and more importantly, how time series is more relevant in today's world, right? So let me get started. So this is how the topic looks like. And I'm going to cover concepts. I'm going to cover some of the use cases. It's going to be an engineering time series systems, because when you talk about time series, it's not about only modeling, right? It's not about only the ARIMA models or Facebook Prophet or even LSTM models. There is a huge engineering effort that goes on before getting into the modeling part of it. So I'll be talking about engineering time series systems, and then as I'm talking through these topics, I will be also covering forecasting techniques and also challenges that we typically face with time series data. That's about it. This is not going to be a detailed session. There is no hands-on session over. It's more like concepts. But after this, if you want to deep dive to any of these concepts with hands-on code, then you can follow my YouTube channel. These are some of the resources where I have a course on time series, and it's in my AI engineering YouTube channel. This is the top one, is the link for all. It's like time series for all. There's also an open book available by Rob Hendman, which you can go and download. It's an excellent book. This covers all the concepts and some of the real world data set and how to use time series techniques. This excellent book. If you want to look anything outside time series, you can also go to my channel and you can check out details on other courses I have. I have courses on natural language processing, computer vision, and model deployment and everything. You can check that out.
So what is time series? Time series is a sequence of information that attaches a time period to each value. In case of time series, the data has a natural temporal ordering. So in this case, if you take a typical ML problem, you have a set of observations. These observations are independent. So you can take a data, you can feed it to the ML algorithm in any order. But in case of time series, the ordering is pretty important. So you cannot have like 2013 data after 2015 or 2014 and before 2012 or something like that, right? You want that order to be maintained, because most of the forecasting techniques you are using, the order is pretty important. It sees the past pattern over time, it sees the seasonal pattern, and then try to forecast or predict a future value. So ordering in this case is very important. right? The other aspect is, in this case, the data is collected in regular intervals. The regular interval can be a microsecond, a millisecond, or a second, hour, day, month, year, or whatever it is, right? Now, most of the cases, you have data continuously coming in from an source system that flow in and in regular intervals. But that is not true in all the cases. You may have even time series data with irregular intervals. And the way you handle irregular interval data is different from the regular interval data, which I'll be talking more as we go into the details of it. Finally, a time series data are append only. So what I say mean append only is the data are typically not restated historically. So you don't go and modify an historical data. 95-96% or more than that time, the data just come into the system and sits as an append only record. You don't go and modify the record. But there might be some cases where maybe the device you are using to capture your time series data may have some issues, and maybe it has given wrong data. You may want to go and restate the data. So that is quite possible. Or you may be missing some records where you want to go and update those records. But most of the time, this is only like append only files over here.
Time series has been there from here more than like 100 of years, right? I think the first application of time series was in the late 1800s. So why is it relevant even more today? Like traditionally, what we do is we use time series for weather forecasting, earthquake modeling, or sales forecasting, inventory management, and a lot of other business process. And these have been running for years. But what we are seeing today is a lot of IoT based devices are deployed, which is capturing data every second or every minute, and it has time order to it. This IoT device are either employed in manufacturing industry, where they are predicting all your machine maintenance and machine data. It is deployed in data centers. Typically, if you see today, the cloud and even within the organization, the data centers are pretty big. There are thousands of servers, and you want to know the real-time information on how the server is performing, what is the CPU usage, what is the network bottleneck, or what is the memory usage. And each of the system are generating data in real time. You typically use some kind of software on each of the system to collect data in real time, right? So the data over here is continuously streaming, and we just want to make sure our application is running, because today applications are defining how the company operates or how the enterprise operates. You don't want it to go down and impact your customers. So you have your data centers, you have your machines that are smart, your smart home appliances, you have self-driving cars today, where it's continuously generating data to know about how the car is performing, how basically the car is kind of reacting to external environment like weather, or even like other conditions where it's completely like foggy or accidents or something like that. So today you can see even more application of time series. And more importantly, you might have heard the term called AI ops, right? Which is how you can enhance your IT operations with the usage of AI and ML. When I say IT operations, you may have your web services or REST APIs running on production that is servicing your customer. There is a possibility that it can go down anytime. You want to capture those events before it goes down, and you want to also correlate with the other system. How is the database that's connecting to performing? How is the external data sources that it connects to performing? So you are kind of aggregating all your data, and you're trying to get insights on whether the application will fail, or do I need to scale the application, or what capacity I need to run to. So that's the reason, like time series as an additional use case today in anomaly detection, or even in high velocity predictive maintenance across industries. Now, how do you typically approach a time series problem, right? If you see, this process is no different from how you approach your machine learning problem, or even deep learning problem, or any other problem. But what typically changes is, in each of this life cycle, the techniques that you use, or the statistical method that you use, or the modeling method that you use is different, right? Now you can also use a traditional machine learning algorithm for time series, but remember, the models like XGBoost, SVM, or others are not time aware. whereas there are models that are time aware as well. So we need to use the right modeling technique for the right problem. And this is a typical life cycle. I'm going to cover in detail some of the life cycle as I go further. But typically what we do, we first frame a problem, right? What am I trying to do over here? Am I trying to detect anomalies, or am I trying to forecast a particular event? Am I trying to forecast sales? If I'm trying to forecast sales, am I trying to forecast the sales for the entire enterprise, or am I doing it at a granular product level, right? So it all depends, because if you're doing it at a product level, a enterprise might have millions of product. If you take Walmart, they have millions of product online. So am I doing at a product level, or am I doing completely at a Walmart level, right? So your problem, you're framing the problem and what you're trying to achieve really dictates how you are going to scale your the pipeline, how you are going to model it, and other aspects of it. Then I go and collect the data, right? Now think about it. If I have to collect the data at a product level, then all these products are generating continuous stream of real-time events. How do I capture the data? Right, and how do I analyze the data? Right, now typically in machine learning we do correlation, or we do other techniques for categorical data, we do exploratory data analysis. You're going to do the same thing over here, but the techniques that you're going to use are completely different, which I will cover as we go to the details. How do I engineer the data? Right, I'm going to talk about it in detail. Then comes the feature engineering. The feature engineering should incorporate a time dimension to it. Right. So when I talk about RFM models, the recency frequency monitoring models, I need to know, like, what is my customer doing in the last 1 week with my products? What is the customer doing last 1 month or 1 year with my product? So I'm generating features that brings in a time attribute of customer recency with my product, customer frequency with my product, right? So that's why the feature engineering comes into play. Then I train the model, I evaluate the model. Now your evaluation is the most complex part. If you're doing it at a product level, then each of the product level time series you need to evaluate and make sure it is performing better. So if you have a million products, you are doing a million evaluation, and a single global model might not fit the entire scenarios. So you end up creating maybe millions of model, or a model at a different categories, right? Then you serve the model, and then you continuously monitor the model. The forecasting models are very difficult to get the best accuracy. That's why you always have a confidence interval in your forecast. Think like a COVID kind of scenario. The forecast models are the most impacted in this scenario compared to your machine learning models. Even the machine learning models are impacted, but in comparison to it, right? So that's where you go back and retrain, reevaluate, and the entire cycle starts again. Right. So let's start with some of the blocks in detail. Right. Let's start with data collection. So a typical example that I have put here is, if you take an aircraft, right? If you take a flight, if you go from, say, A location to B location, on an average, a flight generates 30 GB of data per trip, right? If I'm just considering the average trip of a flight to be 3 hours, but if you take a long distance flight from maybe India to United States, it may run for 24 hours, right? So it generates 30 GB of data per trip and 10 GB of data per hour. It has a lot of information, time series information, like the altitude it is flying, the temperature, the power, the external factors, what was the outside temperature, whatever, was there any turbulence? There are multiple factors that it. If you see on the right hand side, the average flight hour per year that a flight makes is 3,000 hours. And if the data generated is 10 GB per hour, you almost have 30 terabyte of data per year per flight. If you take any airline in this airline today, like biggest airline, like American Airlines has close to 800 flight, Delta has close to 800 flights. There are a lot of airlines have at least 100 flights, right? Now, if you take with 100 flights, you're talking about 3 petabyte of data. For an airline, and you need to analyze that 3 petabyte of data. Now, not only analyzing the 3 petabyte of data, it's only for 1 year I'm talking about. It's 3 petabyte of data per year, right? You need to analyze, and more importantly, you need to collect the data. And what we result is an high velocity streaming data. So it's not like your batch process where data comes and sit and you can take it end of day and put it, right? These are all real-time sensors that are continuously sending data. If you take in a manufacturing industry, the predictive maintenance, each and every mission is basically sending data every second or every milliseconds, right? They're continuously streaming data about the health of the system. Similarly, in data centers, each of your servers or each of your routers are sending data in real time. So you need to capture this high velocity streaming data. There will be complex relationship of pattern. So you take in the flight example, right? As I'm flying in a higher altitude, the airspeed also depends on external factor like temperature, right? So you need to correlate your external factors. So now becomes like a complex event processing system, which is core for any time series, right? And finally, the data will be in multiple formats. So when you connect to your IoT devices, there are specific protocols for it. You have protocols like MQTT or the other protocols, or it can be sometimes just a JSON file coming in. It can be your car diagnostic or OBD device that you connect that continuously sends data to a JSON format to the cloud, which you pull in. So there are a lot of different formats that comes in that you need to take it, structure it, and also analyze it in real time. And typically, this is how an architecture looks like. Okay, so I will come to the architecture. Before that, like before going there, let's also complete the data analysis cycle, right? Because both go hand in hand. Now, data analysis, you typically do a statistical test, and you also do more kind of an exploratory data analysis. Now, when we talk about time series exploratory data analysis, basically there is an auto correlation to data, and you need to check like how my past pattern is affecting the current pattern, and the past pattern is within itself. Say I'm going to predict a temperature tomorrow, right? The temperature typically follows a pattern of previous day or a day before, or if it's a yearly seasonality, it may go to a pattern previous year. So you're doing an auto correlation over that. So you need, when you talk about time series data, you need to understand multiple factors, like is there a trend to data, is there a seasonality to data, is there cyclic nature in the data, right? How does two or more is time series interact? Does an temperature cause electricity demand to spike up, right? Or does kind of an temperature cause all pollutants to go up? So how two time series interact with each other? When you talk about multivariate time series, you need to understand like how two or more time series basically interact. Does X causes Y? Right, that's what we are going to check. And for that, to do that, you have special statistical tests like Granger's causality test to check that out. It's in a typical world, you will just run correlation test, but when there's a time element, the correlation test might not work properly. You need to see whether there are outliers or there are missing data. If there are missing data, how do you impute it? You cannot just impute it by the mean of the entire time series. You need to maybe see if it's a temperature data, I can impute it with the previous hour data, or if there is an other data set, I can impute it based on the seasonality. So the imputation also is different when we talk about time series data. Outliers are different, like because there are two outliers. One is the data outlier, where data is completely outside the range. The second is the context of the outlier. I'll be talking about context of the outlier as when we get there. But these are all some of the data analysis techniques that has to be thought through when we think about time series data. Right, and then this is how your typical data engineering looks like. Right, so on the left hand side, your sources, it can be your application, it can be your smart devices, it can be your self-driving car, it can be your IoT devices, right? And these data are coming in absolute real time. So as and when the event happens, it's generating. Sometimes, like if you capture the event after 1 hour, the event does not make sense. Say if you're capturing a data center and you get data that, okay, that's a 404 or that's an out of memory error. Think about it. If you capture after 1 hour, the system is already down. Your customers are impacted. You need to know about this particular system as and when it happens. Right, and that's where real-time streaming is very important. So you take this data, you collect into a streaming platform. The streaming platform can be even your message queues, it can be Apache Kafka, it can be anything, right? Whatever that works for your scalability need and your high velocity need, right? So once you have the streaming platform, you need to process this set of streams. When I say process that of streams, sometimes there are two ways you can do analytics. You can do in-stream analytics, you can do batch analytics. So batch analytics is basically you take the data, you store the data, and then analyze patterns. That's what we typically do when we model it. But in-stream analytics is as the data comes in, you want to run your model in real time. You want to run your analysis in real time. And that's where the stream processor component, it can be Spark streaming, it can be Apache Flink, or it can be any cloud services like Cloud Data Flow, or in AWS, the equivalent component is that it can be Kinesis, and it can be some kind of stream processing component in AWS. It can be even Lambda. Right, so you have to run this stream processing in real time and also capture the data in a low latency store for doing a near real time analysis, and also in a batch store where you are doing like offline analysis, like you're building models or you're building some dashboards, or the dashboards can be done in the NoSQL as well. So that's the connection from year to year. So you're kind of having a component that can get data in real time, that can act on data in real time, that can correlate in real time. Say you are temperature data coming in and you are like self-driving car data coming in. You need to take the stored data and then correlate it. So at at this X time, what was the temperature when the car went into an accident? Right, maybe they are driving at 70 miles per hour and it was snowing over there. The self-driving car did not react to the temperature. You want to do an analysis on why this happened. You need to correlate data. Right, and finally you use the data lake, data in the data lake that is more like batch oriented, to build your analytics and models, and then pass those models and deploy it in the stream processing component, so that as and when data comes in, you act in real time. So this is how typically your engineering pipeline looks like, and this is a key part in any time series system. We typically miss this part and we focus only on the models. We focus on building like models after the data is stored, but in real world, the data will have to go through all the system before we even get it to model. Right, so that's where the data engineering pipes into comes play. Now, there's one more important aspect of it. How do you store the data? Now, typically when we do deal with time series data, we get the data in a CSV file. And the CSV file is good for modeling, right? You have like decent sized data, you can put it in a CSV file, you can run your models. But what if I want to do an what if analysis? I know my server was down between 2 o'clock to 3 o'clock on a particular day, and I have say like a petabyte of data. I want to just pick the 2 o'clock to 3 o'clock data, and I need to correlate with other systems and see a chain of events on what happened for my system to go down. Or a cyber security, a hacker came into the system at say like 1 o'clock and you did not realize it. But between that 1 o'clock to 2 o'clock on a particular day, how do I go and fetch that data? If you have a CSV file, it's going to be very difficult when the data is pretty huge. If you have a database, you need to go and fire SQL queries on a subset or substring of the timestamp. It's going to be very difficult and time consuming to pull the data. You want something that can act fast. And that's where the NoSQL store comes into play. Basically, the way you model your NoSQL is also very important, and there are two ways of modeling it. This is the normal way of modeling a relational database. It's called narrow tables. So what you do is you have a time as a column, and the time series ID can be it can be a server or it can be a product. Right now, say Walmart example I was talking about, each product is a different time series altogether. So product 1 can be home appliance, product 2 can be an fabric. So these are the time series IDs, and you insert each observation as a row. This is one way of modeling it. But if I say like if I have millions of product, right, and if I have data captured for 5 years, my table will be relatively very, very huge. And for me to run the query for an hour will take a lot of time. So that's where a wide table modeling comes into play. Typically, it's more applicable in the NoSQL database. What you're doing in this case is a NoSQL databases works like a key value pair. So key value pair, if you work with Java, hash maps and everything, is nothing but a key value pair, right? So in the key value pair, what you do is you define your keys as time series ID and date. So now if I want to go and pick a data for home appliance, I can just do where time series ID equal to 101. and what date I want. I want to pull data at 5 o'clock in this case. So I go to 5 o'clock, and between 5 o'clock to 6 o'clock, I want to pull. I just take this, and each of my data point, in this case, the data point is every 10 minutes, right? That is at 5 o'clock, 5:10, 5:20. Each of my data point is at a column over there, not a row. So if I just query by this, I get the entire data, and then I can do what if analysis. And this key value lookup is very fast. It's a distributed system. Distributed NoSQL database is typically a distributed key value store. It is very fast because it exactly knows where the data is. Now, when you are doing for analysis, or when you are doing for backtracing, what if analysis, you also need to think about how the data needs to be stored, which typically, like, many will miss in designing time series systems. Now, coming back to what are the methods of modeling a time series data, right? We spoke about data engineering. We spoke about data collection. We spoke about data analysis. We spoke about data engineering. Now, once you are done all that, you come to your modeling part of it, right? And the data engineering is also about building aggregates. It's not only about the raw data. Basically, in the stream processor, you also create aggregates. What is the last 3 hours customer spend? What is the last 2 hour customer spend? So you create a lot of features, and these features can be used in your machine learning model. If you take a typical credit card fraud model, right? How do you determine whether a transaction is a fraud or not? You generate multiple features of a customer attribute. So if a customer has done, like, the customer last 2 hours spend is $100, and customer last 5 days spend is $200, customer last 1 month spend is $1,000, and suddenly he goes and swipe and makes a $10,000 purchase, then it's an anomalous pattern as per the customer behavior. So that can be a fraud. Then you try to correlate with other attributes, right? And that's how you do. So these features that you build are also done in the engineering pipeline. Apart from the features, you also build doing the modeling process, right? So when we talk about modeling, you have multiple ways when you talk about time series, right? So when you talk about what will be the future value of my particular time series, right? And that's why the forecasting comes into play. Basically, you're forecasting your data for a period forward. The second aspect is what category a time series belongs to. So you may have, like, in the healthcare, typically you have ECGs. A ECG is nothing but you're monitoring your heartbeat rate, and the heartbeat rate can go multiple patterns. Now, there are like 6 to 7 patterns in which a heartbeat is measured, and to predict which pattern it is, you can use a time series classification techniques over here. Now, does the incoming data has abnormal behavior, right? You want to do anomaly detection. So when does my server spike? If it spikes above some 2 times the standard deviation or 1 time the standard deviation, you want to alert your systems. And that's where the anomaly detection comes into play. How does your data change over time? Does the mean, the standard deviation, the variance of data change over time? You are just doing analysis over there. So this sometimes you just need analysis to deploy your insights. You don't really need a model, because if you take a stock market, it's really, I know everybody likes to play with stock market, build model, but stock market are difficult to model. If like stock market was easy to model, every data scientist would have been rich today, right? But that's a difficult part. Sometimes you just want to do analysis and see, like, maybe run typical moving averages or exponential moving averages analysis, right? The final thing is intervention analysis. Now, intervention analysis is how the mean level or the variance level of the series changes after the intervention. Now, intervention, the classical example today is your pandemic, right? Coronavirus. What happened to forecasting models? The forecasting models completely changed behavior. The mean of the time series has completely changed for some of the industry. For some industry, it has done positive. If you take online retailers, they are benefiting from it. But what happened to the in-store retailers? They are completely gone down. So this intervention analysis to analyze whether a pandemic or a policy or a procedure has affected the time series. I'm going to talk each of it as we go into the details of it, but these are different way you can do time series analysis and modeling. There's other things also. How do you impute a missing value? How do you correct the outliers? So all these are also there, which comes at part of the analysis phase. Right now, what is time series forecasting, right? So time series forecasting is nothing but you take your past behavior and you try to get model your future pattern, right? So you can take the past sales, and based on the past sales, you can predict the future sales of a product. Now, when we talk about the present is the current time t, right? And the past is basically the current time t minus 1, t minus 2, t minus 3, till t minus n, till the duration you have captured the data. Now you take this data, you model it. There are multiple ways of modeling it. You can use an AR model, MR model, ARIMA model, ETS, or even LSTM, Facebook Profit. There are a lot of ways of modeling it. I will get there. But you take the past data, and then you take the past data and predict the future data. Now the future data can be a single step. That means I can take this data and I can predict tomorrow's sale, right? Sometimes like that's not enough. I want to predict like next 10 days sale or 3 months sale, and that's where the multi-step forecasting comes into play. So there's a single step, there's a multi-step, right? So the time series forecasting basically taking past data, which are observed values or collected values, and predict the future value, right? Now, a time series pattern is very important, or very much possible only if the data has a pattern. If the data is random, or data is just a random walk or a white noise, it is very difficult to model, right? So there is some assumption that we make when on what we can forecast. There needs to be some kind of pattern, which I'm going to talk about now. One thing is that for the future to be predicted, the data has to be correlated. It has to be auto-correlated as well as correlated with the other variables, right? Now, the way we capture data is we can capture data at every minute level, or every hour level, or every like a day level, or even month level. And your forecasting also can be done only at that granularity. I cannot take a monthly collected data and do forecasting for the next day. So it's very important to understand like how your data is collected over here. If you already have an aggregated data, then you can only do an aggregated forecasting, right? So the core concepts of time series is basically, first is when you take a time series data top over here, the data is nothing but a combination of trend, seasonality, and the residual. Now residual is nothing but when you're trying to decompose the data, right? You have a data element. The data has a trend in it. That can be upward trend or a downward trend. During coronavirus, the online retailers saw an upward trend in sales, whereas the in-shop retailers saw a complete downward trend in sales. The reason is most of the shop was closed during the lockdown, right? So there is a trend component to it. There is a seasonality to it. Typically during the holiday season, the retailers will see spike in sales, like it's a Thanksgiving or Christmas or New Year or Diwali. We will see a spike in sales, but after that the sales will be normal. So this happens every year. This year Diwali it might happen, this year New Year it might happen, last year Diwali or New Year it has happened. So there's a seasonality to it. So when we break a time series, you have a trend and seasonality, and not everything can be captured by trend and seasonality, and the remaining is called the residual. So there are two types when you take a time series, right? You have additive and multiplicative. Now, additive is basically when the variation around the trend cycle, this trend cycle variation, I'm going to show some examples as we go into the details. All the magnitude of the seasonal fluctuations does not vary. Yeah, it's constant across the time. We call it an additive time series. Or we call it additive decomposition or multiplicative decomposition. If you see any statistical methods that you use, if you are using the stat model package of Python or any R package, you have to understand whether it's additive or multiplicative. You have to feed that, and then only you will get a decomposition output. You can also convert a multiplicative seasonality. So additive seasonality is nothing but your trend plus seasonality plus residual. Your multiplicative is just multiplied by 3, and you can convert a multiplicative seasonality to an additive, because additive is easy to understand by taking a logarithmic. So you can take a log of each of this variable and you can model this as a additive variable. And what you need to do is, after you have modeled it, you need to basically reverse the logarithm expression to get the original value. You can do that as well. Right. So one of the key part is when you have a time series, you need to understand the different component of time series. If you're using a Facebook Profit, and when you just print the output of the model, it will give you all this chart by default. But if you are using some statistical libraries like Python, you have to do this and then feed it to ARIMA or some other model. right? So you need to first decompose the time series. Now a data might have trend, the data might have seasonality. One of the key thing is any of the statistical models that we use like EAR, autoregressive or moving average model or other models, or even the statistical text like Granger's causality assumes your data to be stationary. So what does stationary mean? The stationary mean the mean is constant, the variance is constant, and there's no seasonality and trend. So if you have to fit an ARIMA model or ARMA model, I will come to ARIMA model later. If you have to fit a ARMA model, AR-MM model, auto-regressive and moving average, or even individual AR and MM model, you need to make sure the data is stationary. Now, when a data has trend or seasonality, it says it's not stationary. When the data mean is not constant, it's not stationary, right? Now, how do you see whether it's a stationary or not? On the right-hand side, you have two graphs. The first graph, if you see, the data is centered around the zero mean. If I draw a line on zero, right, all my data points are going up and down, but it's centered around zero over here. So this particular time series is stationary because its mean is constant around zero. The variance is also not like very much up and down, the slight up and down, but that's fine, right? There seems to be some seasonality, but the seasonality is not really consistent in all the places. Now there are two types of or multiple types of stationary. There can be a strong stationary, weak stationary, or trend stationary. So your model need not be strong stationary. Strong stationary has to meet all these conditions. And if you meet all these conditions, then typically you will end up like this, like a white noise. And this is a white noise, and white noise cannot be modeled. So if you have a data something like this, which does not have any pattern, which does not have seasonality, it's very difficult to model the scenario. So your data can only be weak stationary. I'm going to talk about it more as we get into the details. And what is a non-stationary? If you see in this case, if I draw a center line, my data is not touching my mean. The year in this, assuming the mean is minus 40. The data is going up and down. There seems to be some downward trend and upward trend. So in this case, the data is not stationary because it's not constant around the mean, right? So it's not stationary. So it's a very important concept to understand whether the data is stationary or not. Now, if the data is not stationary, what you do is you make it stationary. And how do you make it stationary? Is if your data has a trend. Right, in this case, what is trend, right? In this case, assume this is the international air travel between 1949 and 1961. So if you see the air travel is continuously increasing over time. That is a trend. That is a positive upward trend. If you take Amazon quarterly revenue, you will see like positive upward trend. In this case, the data has a trend. The variance is also not constant. If you see initially, the seasonality peak is small, and as it goes, the seasonality peak also increases. So if I fit a line, I am fitting a line like this, and there's a positive trend over here. And the seasonality is also varying. So this is how the trend data looks like. In order for me to make this stationary, which centered around some mean, what I do is I take a difference. I take the last y of t value and differ it with the previous y of t minus 1 value. That is called first order difference. When I make a first order difference, my data can become stationary. But how do I test whether the data is stationary or not? You can do a visual analysis whether it's stationary or not, or you can run some statistical test. There are tests like KPSS test or augmented Dickey-Fuller test, where you can test an hypothesis whether a time series is stationary or not. Now, sometimes even after taking the first order difference, the data might not be stationary. So you go ahead and take another order difference that is called second order difference. So you do a y of t minus y of t minus 1, and then minus y of t minus 1 and y of t minus 2. Right. So basically you're taking previous time series and you are basically doing the difference. Now, in this case, most probably in 98% of the cases, first order and second order difference should do. In some cases, you may have to go for third order difference and higher order difference, but it's very rare scenario. Now, if you take ARMA model, the data has to be made stationary. So you apply this difference, right? Now, that's where the ARIMA model comes into play. ARIMA is nothing but auto-regressive integrated moving average. Now, the I component is where the integrated part as a parameter called D. So if you see like P, D, Q, P is for auto-regressive, D is for integrated, and Q is for your MA models. The D parameter is nothing but the differencing. So you are telling 1 for first order difference, 2 for second order difference, and so on. So ARIMA, that's why it's called like auto-regressive integrated. So you don't have to do your differencing outside. You just understand the pattern and you set the I parameter so that the ARIMA model can do it by itself, right? And non-statistical models or any kind of advanced model, LSTM or something like that, are less prone to it. But it's always better to do the difference so that you can understand and explain your model better, right? Even though they are not that explainable, right? So this is the trend part of it. Now the second part is seasonality. Now, this is where the additive and multiplicative, how do you find out whether it's an additive seasonality or multiplicative seasonality? So if you see on the top, right, so that is a seasonal pattern. You can see like the time is between 0 to 96, and every 6 months, right, you are seeing some kind of seasonality up and down. That's why every year, I'm sorry, so 12 and 25 every year, it's a month level data, you're seeing some seasonality. In this case, if you see this particular, there is no fluctuation in the seasonality or there's no fluctuation in the trend. And that's why it's called additive seasonality, right? There's no fluctuation, it's constant. Now, in this case, if you see, there is a trend. But again, the variance in the trend is not fluctuating. The variance in the trend is constant, right? If you see the previous slide, in this case, the variance in the trend was not constant. The variance in the trend was fluctuating. So basically, this is a multiplicative seasonality. But in this case, there's no fluctuation. So it's an additive seasonality, right? So there's no variation around the trend cycle. And if you see multiplicative, there is seasonality over here every month. But if you see the way in this case, there is like variance every month. So zero first year, you have less variance, then the variance keep on increasing, but the data is still centered around mean, but there is variance. So this is multiplicative seasonality with no trend. And here there is a trend as well. If you see the data is moving, it's not centered around mean. It's moving up, there's slight positive trend, and there is variance as well. So this is multiplicative seasonality with trend. So this is how you see whether there is an additive seasonality or there is a multiplicative seasonality. And I know I'm talking to a lot of concepts here. Time series unfortunately has plenty of concepts, right? And it's very important to know the concepts when you're doing the time series modeling. I'm not able to go too much detail because of the time, but as I said, like you can go and hit my course where I have covered this in high length and details, right? I want to just use 45 minutes and keep remaining 15 minutes for questions. So I'm just moving a little faster. Now you found out your trend, you found out your seasonality, you got your stationary aspect of it. Or if the data is not stationary, you just take a difference to make it stationary. Now you will typically come across two things, right? The univariate time series, multivariate, and also multiple time series, and within multiple time series, multiple multivariate time series. So in univariate time series, basically the response variable is influenced by only one factor. Let's take this example below. So this is, I have data on a daily basis. I have multiple features. I have PM 2.5, temperature and pressure. And PM 2.5 is nothing but the air pollutants, right? Typically, if you take the weather in Beijing or Delhi or any of the places, during the winter, the air pollutants will be very high. You can see in Delhi, basically during winter, you will have low visibility, and that's because of the air pollutants. That is the PM 2.5. So during winter, the PM 2.5 is pretty high, and there's temperature and there's pressure. If I am modeling the PM 2.5 only based on the past values of the value, then it's kind of a univariate analysis. I'm not using any other factor. It is influenced by itself, by this one factor. But in some cases, my temperature contributes to PM 2.5. The air pressure contributes to PM 2.5. And this is where you enter into multivariate time series. Basically, the response variable PM 2.5 is influenced by multiple factors here. Now, there's one more thing. How do you know whether this factor contributes to PM 2.5? This factor contributes. When you're running a multivariate time series, if you take a typical machine learning, you tend to throw in a lot of features and see like where the feature work. But in multivariate time series, you need to make sure you need to keep only relevant features. The reason is, now say I have data till 2013. I want to predict for 2014. Now, I don't know the value of temperature in 2014. I don't know the value of pressure in 2014 to predict PM 2.5. So what I need to do is I need to first build a model to predict temperature, predict pressure, and then use that and predict the PM 2.5. Or in this case, I can go to external data providers and get the data. But think like if you are having some other data that is, say in the sales forecasting, I need to predict customer footing. How many customers will walk into my store. It's very difficult. You cannot predict it. So you need to maybe build a model and assume with lot of confidence that this will be the value. So you need to predict first and then use it. Now this prediction, in this case, the temperature pressure may have a lot of error. You can fail predicting the temperature. You can fail predicting the pressure. And if you fail predicting it, your PM 2.5 prediction will also fail. And that's where you enter into a confidence range and you kind of run simulation models. And that's where your Monte Carlo simulation along with time series does. And that's what a lot of forecasting projects do. They run simulation to predict your other variables so that you can model your original target variable. Right. So multivariate time series, you need to make sure this temperature really contributes to PM 2.5. If it contributes, keep it. Does pressure really contribute to 2.5? Contributes, keep it. And how do you do that? That's where the Granger's causality test comes into play, where it will tell whether the temperature causes PM 2.5 or a pressure causes PM 2.5. So that's again a statistical test that you can run. Right. Now, multiple time series. Now, multiple time series is even harder. Like multivariate, I was talking about. There's multiple multivariate time series. So, take example of Walmart. Right. Now, Walmart has 11,000 plus stores, and it has like close to 120,000 product in each of its Walmart super centers. It has 35 million product online in 27 countries. Now, if I have to run, if I need to develop a model to forecast the sale of each and every product, right? I have to do like in the case of in-store, let's forget online for now. I need to develop 120,000 models because I cannot develop one global model. I need to take individual time series by itself. I need to model it. It's not like machine learning where I can do like 120,000 modeling at one stretch. You can still do it as a machine learning problem by defining features. One of the point I said is, if you take a traditional ML model like XGBoost or SVM, they are not time aware. And that's where what you can do is you can make them time aware. How do you make them time aware? By generating features. What features? Typically, what the statistical model do is they compute lag of the particular time series. Like in the case, I am predicting a forecast for a shirt, a particular type of shirt, say like it's Adidas shirt. And then in this case, what I'm doing, I'm checking like how was the sale in lag 1, lag 2, in the previous seasonal lag, and then I create features, and then I can feed it to an XGBoost model so that I can make my XGBoost model time aware by feature engineering. But that's not going to be perfect, right? You can do it. You may get a lot of better results the more features you put in, and that is time cumbersome. Other option is I can run time aware model like Facebook Prophet, Arima, and that's where I need to model each of this as a separate time series. There are some new models like Dphi, which is nothing but deep auto-regressive model, which was created to create like one global model for a time series. But the one global model might not be perfect because it will get influenced by other products as well. So within Dphi, you can also define multiple local models, but that makes the modeling easy, but still you have the problem of creating multiple models. So now you are creating 120,000 models. Now, when you are modeling itself, you need to make sure your modeling scales, because when you are running 120,000 models, you want to run everything in parallel. If you take weather forecasting, I have thousands, I have 100,000 or 200,000 plus zip codes in a country. I have to run for each zip code what is going to be weather, or within the zip code, each locality what is going to be weather. So I need to scale it, and that's where your distributed computing comes into play, like Apache Spark or other distributed computing where you can scale your multiple time series modeling, right? So you need to remember this, right? Your scale to predict for each product location is very important. Now within the product, like I have a shirt, I need to know which color shirt I need to order. So I need to prepare a time series model for blue color shirt, pink color shirt, yellow color shirt, white color shirt. Now, if I say, okay, I am predicting like there will be, I need 1,000 shirt to be ordered. But if I don't predict the color, I may order all colors in equal. The pink and yellow might not go as fast as the white and blue. So again, you may have a problem. So that's where like multiple time series is very challenging. You need to back test and validate each of these time series. You need to accommodate different market condition and changing customer behaviors and multiple other aspect of it, right? So the next part, this is about time series forecasting. All I was talking about is time series forecasting. These are multiple things that you need to take care of. Classification. The classification aspect of it is a typical example of ECG I was talking about. If you see, based on the ECG for that is captured, there can be multiple pattern. First is the normal pattern and remaining are abnormal pattern. And within abnormal pattern, each time series has different, there's an RNT time series, this PVC time series. So when you're taking a ECG, now you want to predict whether it's a normal or abnormal, and within abnormal, what category it is. And that's where the time series classification comes into play. Basically, you can either model this as a typical machine learning model XY, or you can even model this as a time series model and see which classification it falls into. Right. More ideally, the machine learning models will work fine. Typically, your XGBoost model or other models might work fine once you know the data embedding pattern, right? Because each of this is a time element, and you can take the time element and can model it, right? So that is one aspect of it. The next is anomaly detection. When we talk about anomaly detection, there are two parts to it. There are data outliers, there are contextual outliers. Now, this is a time series that was created for New York taxi cab. If you see this time series, some of the points are modeled red, right? In this case, if you see, this looks like really outside of the normal data pattern, right? But think about this one. This is marked as anomaly, but it does not look typically outside of the pattern. But how is this anomaly? This is a contextual outlier. Now, if you see below, this data is from October 2014 to Jan 25th, 2014. This our data is available online as well. You can go to my Git repo, and I have details on where you can find the data and everything. So in this case, how is this context? So if you see the date, it was January 1st. Now, if the New York taxi ride in this case, typically after night 1 o'clock, the number of taxi running are pretty low because people don't take taxi during the early morning or during the late night, right? But in this case, it was January 1st, and in New York, basically Times Square is very live. And in this case, you can see the taxi rides were pretty high, and that's why it's an anomaly, but it is a contextual anomaly. So you don't want to take this value and really think next week also I will have this much sales. It is only an event that has caused it. And that's how you got it, this anomaly. In fact, this code itself, how you need to model it, I have it in my time series for all, the bit.ly link I had given in the initial video. You can go and check it out. So this is anomaly detection. Anomaly detection is pretty common today with your machines. You want to know when the machine will fail. So you're checking for anomalous pattern. You're checking for other aspects of it, right? This is where the time series anomaly comes into play. The second is intervention analysis. Now, intervention analysis is basically how the mean level of a series changes after an intervention. So in this case, let's say this was the latest data that was shared by JP Morgan. And if you see in the bottom, you have your January to November data. And in around March, we saw a pandemic, right? And if you see over here, there are two graphs. One is card present and card not present. This is the credit card sales, credit card usage, JP Morgan credit card usage. Now, what is card present is you go to in-store and you swipe your credit card. That means your card is with you. That's called card present. You shop online. You don't really use your card. You just key in the card. That's card not present. So any sale where you don't need a physical card, that's card not present. Otherwise, it's card present. If you see over here, before March, almost they were close, the card present and card not present. But after the pandemic started, the card present literally fell and the card not present was around the same line, or it even increased in between. The reason is all the shops were closed, or people were scared of going outside due to the pandemic, and most of the people were using online services. So in this case, there's an intervention, and there is an external pandemic that is causing it. Now, if you take the other side of it, right, not only because of the pandemic, the same card not present and card present, if you take from the fraud scenario, so that there was a EMV chip that was introduced in credit card a decade back. If you see today, all credit card has a EMV chip. You don't swipe the credit card. You sometimes insert it. You most of the time insert it. So before that, there was no EMV chip. So all the fraud that was pretty high was in the card present. So what will happen when you go to a store? The merchant can skim the credit card and use it in a wrong way. But after the EMV was introduced, the card not present fraud increased and the card present for fell down. So there was an intervention. The intervention in this case was introduction of EMV chips in the credit card. And similarly, this one other product of North Carolina accident rate. So if you see, the accident rate has been like constant, ups and down, but all of a sudden, around like 67th or 78 times, yes, it started dropping down. And what was the problem in this case is the accident rates were pretty high. The speed limit at that time was 75 miles per hour on this highway, but they reduced the speed limit on the highway to 60 miles per hour. And you can see basically it's completely down, the fatality rate, right? If you are not considering the intervention analysis over here on why it cost, and if you start modeling it, then your forecast will go. So it's very important you do intervention analysis on what costs this particular time series to fall down. Now, this is where the concept called endogenous and exogenous variables comes into play. Endogenous, something that it can be impacted by your known factor. Exogenous can be unknown known factor, right? So that's a separate concept maybe you want to learn. And that's about it. I will open up for questions now. But anything else, you can go and look it online, or if you have something, you can just reach out to me in my LinkedIn account.
Thanks a lot, Srivatsan. I think it was very insightful. And also, we have a lot of questions, so probably I'll pick one by one from YouTube. So first question is, how do you deal with huge class imbalance due to granular data from sensors?
So see, the class imbalance is how you model it, right? Now, what is your purpose? Typically, if you take a sensor, you may have typically a machine, predictive maintenance. Your machine is fitted with a sensor and it's getting data. Most of the time, it will be normal behavior. Now, abnormal behavior can be a 1 in million chances, or 1 in 10 million or 20 million chances. So yes, most of your data is going to be abnormal, but what you're trying to model it, if you're trying to model when my system is giving an abnormal behavior, you can use like anomaly detection algorithms like autoencoders. So what autoencoders we do is we take our data, we feed the normal behavioral data into autoencoders and kind of learn from the normal behavior. And the abnormal behavior is just we pass to the autoencoders. It will show a different pattern, something called reconstruction loss. It's going to show an higher reconstruction loss and then predict it. So there are ways of modeling it. You can aggregate the data as other option if you want to run a typical time series forecasting. You can aggregate the data from millisecond level to month or year level, or you can deal it as a typical machine learning problem where you can feature engineer and feed the data. So there are multiple approaches depending on what you are trying to solve.
Yeah, got it. Yeah. And when do we decide between time series versus normal ML model, like regression for a time series?
So see, like the major difference is time series has an time element attached to it. When really time matters, I want to predict the weather tomorrow, whether it's going to rain or whether it's going to snow. I don't care about the time it's going to happen. I can just run a typical machine learning problem based on past pattern. But I want to exactly know at what time it will do and what will be my weather at 6 o'clock, 7 o'clock, 8 o'clock. What is the probability of my prediction whether it will snow? That's when you need a time series. So basically, if you have time element attached to your forecast, you are dealing with a typically time series problem.
Right. Yeah. And I think there's a follow-up question on this. If our interest is not in forecasting, but just on descriptors, like trying to understand the trend of a product, then can we just use linear regression, for example, to figure out if it has upward trend or downward trend?
Yes, you can. You
Yeah.
don't. You can even use simple statistical techniques. Now, what does auto-regressive mean? Internally, if you see like auto-regressive or a VAR model, they are not. They are nothing but regression models, right? So, if you are this was related to the imbalanced data, right? You're talking about.
Yeah, I think so. I mean, like,
Okay.
probably like it's just a specific interest. Maybe it's like a
Okay.
yes or no
So
question.
yes, you can capture the mean and variance, and you can even run simple t-test or something like that to see the incoming data is different. You can your analysis can be on multiple chunks and patterns of data as well. So
Yeah,
yes, you can do that.
great. And yeah, I'm doing a project on time series, and for thousands of data, it is sampled at five minutes time frame. But sometimes data is sampled at 7 to 8 minutes. How do you typically handle this?
So see, like what you can do is you can average the data to something that is close by, right? Maybe you can bring all the data to same standard, but if within the 7 to 8 minutes, right? If your data is, see, what you have is a irregular time series capture. Now you can convert this into a machine learning problem. That second aspect is you can completely forget and just aggregate the entire data to day level, right? Or you can, if your data does not have much mean and variance difference between 5 minutes and 7 to 8 minutes, you can just consider everything as 5 minutes or 8 minutes, and you can model it. So it's a case by case scenario that typically you need to deal with in this case.
Right. Yeah. And can you forecast forward beyond the number of periods in your past data?
Your forecasting, future forecasting, you can do to any level, but how good it will be, nobody knows,
Right.
right? So that's where your back testing comes into play. So when you are doing a forecasting, you will do multiple back testing and see what is the confidence of each and every forecast. Typically when you forecast, the closer forecast will be better, but as the forecast goes, it will not be that great. So you need to see your model. If your model is completely constant every time, so you, and it has a known cycle, yes, you will be able to, but real world data is not. So it is, again, you, when you are evaluating your model, you need to understand how well you can forecast the future. If you are not able to forecast, no, you cannot.
Got it. And what could be the possible unsupervised algorithms or the strategy that can be used to detect an anomaly in a multivariate time series setup?
So the one good algorithm which I like, which when you are decent sized data, is autoencoders. They are very easy to run. So that is one part. You can also kind of use Facebook Prophet to detect. See, what you're trying to do is in anomaly, right? You are just capturing the mean and variance across your data. And if anything, something is more than two standard deviation or one standard deviation or three standard deviation, according to your business knowledge, you're turning this as outliers. So any of the modeling that you have can be converted into an anomaly detection problem. Even you can use the regular ARIMA also. So it is not like but if you ask me what I like from unsupervised, I like autoencoders, and it has worked in a lot of cases for me.
Okay, great, great. And how do we consider external factors while doing time series analysis? And how do you read seasonality signal?
So your external factors, when you say external factors, you're talking about exogenous variables, which are outside of your business process, right? A consumer spending, I hope that is what you're asking for. A consumer spending can impact your sales, which is completely separate, right? Or a other customer taste or customer behavior can impact, right? Now, what happened to Nokia? They were not ready for touchscreen, and the others flooded. So the market scenario changes. So there are some possibility that you can estimate, some possibility you cannot. So what you do is, when you know like some of the variables, like an economic factor or an consumer spending factor can kind of impact your model. That's where you run your simulations. You need to know what will happen if my consumer spending comes down by 10%. How will my model behave? What if my consumer spending goes up by 20%? How my model? So you're using those factors into your model indirectly as a simulation variable to understand the confidence range, and that's what you typically do.
Right, got it. And how to find whether the data is additive or multiplicative?
So I mentioned, right, when you talk
Yeah.
about additive, you are like seasonality or your trend variance is completely constant across time. So if you take the time interval of 2 years, you will not see much variance in your seasonality as well as your trend. It's going to be constant. But if you see it's constant, you can assume it's going to be like multiplicative, right? Sometimes you can fit it. See, none of the statistical tests are perfect. It will just give you an indication. Sometimes, a lot of time, at least the multiplicative and this one, you can just set it as a hyperparameter and you can see the model performance output. If you take Facebook model, you can, when you are doing a fit method, you can pass when you are defining the model, you can tell whether it's additive or multiplicative. Just run for both and see how it performs. The best thing, this is an easy part. When you're seeing the chart itself, you will be some lot of times you will be able to infer from it.
Right. And there is a follow-up question to that. Is it possible to have additive for a range of period and then multiplicative in another period range within the same set of time series data? How do you
Yes.
approach in such a case?
Yes, it's very much possible. Now we need to think like this additive or this multiplicative, and this is where the intervention analysis comes into play, right? Was it a factor that was driven by your business? What is an external factor? Or it was just like an small spike that you see additive and it will be back to the old one. Take the COVID scenario, right? You may see some pattern in that case. So what you want to do, what is your recovery cycle? And that's where your econometrics come into play. Are you seeing this pattern continue in the future? Then you just take only that part of the model and then forecast it. Are you going to see this a temporary behavior? So see how you can use weightages to your additive and maybe underweight it so that you can forecast the future better. Right? So that is something you can do.
Great. And can you please throw some light on Dickey-Fuller test, which you mentioned? Yeah.
Yeah,
During
sure.
the session. Yeah.
So there are two tests, right? When you talk about stationarity, there are two tests or three tests rather. I typically prefer ADF, which is augmented Dickey-Fuller, and KPSS. Each has a null hypothesis and an alternate hypothesis, right? I think like the I forgot the both the tests are different in the null hypothesis. One of them has like the basically the null hypothesis is the data as a unit root and is kind of not stationary. Other is stationary. So I don't remember it, but you can check it online. So what you do is you feed your data to ADF. You also need to tell the ADF or KPSS whether you have seeing a constant trend or an trend or just a constant data, and then it will give you an p-value. So you can set your p-value threshold, and if the p-value is less than 0.05, you basically reject your hypothesis and go for the alternate hypothesis. So that's ADF, and KPSS is the same process, but it's just alternate how you frame your hypothesis assumptions.
Okay, got it. We have a question from Dr. Nisha Arora. So you didn't talk about cyclic component, which is really difficult to identify. Any thought on that?
Yeah, that's why I did not talk. Okay. So
Okay.
cyclic is see the cyclic is kind of a phenomena with your external factors itself, right? Now, the only thing you can know if you take like an commodity like steel or oil or something like that, those have bearing to other external factors. The oil prices can drop if other factors are getting impacted, if the economy is going down. If the oil prices or economy is going down, the gold prices can shoot up. So sometimes this cyclic depends on external factor, or cyclic can be a business cycle as well. So when the steel or a company uses steel as raw material, when the steel prices go up, then your business revenue can come down because your margins are impacted. So there is no direct way of really finding out unless you use your domain knowledge to it to understand it's cyclic in nature. It's a difficult part to really. That's why not a lot of people talk about it online as well, because it's all contextual to your business.
Okay. Yeah. Got it. And And also, like, some of the people were interested towards time series analysis on inventory management. So do you have any references, or like, do you recommend reading something for them
I am
regarding inventory management time series?
I'm not sure specifically on inventory.
Okay, okay, no problem. Yeah. And okay, there are some career related questions. What kind of questions you can expect in an interview when it comes to time series forecasting? And can you suggest some projects that one need to work on to build their profile?
So you have a lot of time series data today. If you go to UCI repository, there are a lot of time series data. One part I did not emphasize a lot on is even the engineering aspect of it. Somebody looking for a career, you need to know time series databases. Now, when you talk about NoSQL, there are specific databases for storing time series like InfluxDB or OpenTSDB or others. Or there are regular NoSQL databases like Cassandra or HBase where you can model it as white table, right? That is from the engineering part of it. Now, coming to modeling part of it, most of the models that are running time series model are statistical models. I know, like, we all like to do an LSTM forecast and deep learning and all, but you go to real world, the statistics is very important from your analysis phase till the modeling phase. And all this, once you go for a statistical model, you're working on a lot of assumptions. Your data is stationary, your data is trend stationary, weak stationary. There are a lot of assumptions that you need to make and how to handle it. So if you're preparing yourself for an interview, take a data set and try to work with your regular statistical models. Some part I did not cover is like partial autocorrelation plot and autocorrelation functions and how those kind of things. Those are all something very important for you to learn if you are to really focus your career on time series, right? And that's the reason, if you see, you will not find a lot of course on time series, because it's easy to build a course in machine learning and attract people. Time series is more from analysis and statistics.
Yeah, true. And before we wind up, we will probably take couple of more questions if you have time. I
Yes,
think
sir.
like there are plenty of questions, but yeah. So how do we develop a forecasting model for random fluctuations of pattern data?
How random fluctuations of so you mean your data has a lot of fluctuations,
Yes, yes,
and how
random
you can
fluctuations.
do, see, one thing what you can do is you need to first find the components of seasonality. Is the fluctuation a constant or either a trend or seasonality? You can also take the fluctuation, you can normalize the data. See, once you apply your logarithm function to model, your the main purpose of log function is to reduce your variance in the data. You can use log function, you can model it, and you can apply a reverse log function, and you can use that for forecasting. Because your model might not be able to handle a lot of fluctuations. Your model is statistical test, so it depends on mean and variance. If your mean and variance is continuously changing, then your model is not going to be performant or for forecast. So that is one way of doing it. The second is you can also convert that into an typical machine learning problem. So wherever you have fluctuations, and these fluctuations are pretty much reasonable for your business process, you can define various time series features over here. Like what is the last 6 days product sale, what is the last 12 days product sale, 24 days. So you are creating these features to capture that fluctuation. Either you can use these features as your as additional variables or inside kind of additional regressor variables to your model, or it can be typical XGBoost model features as well, right? Holiday is one of the thing. Every holiday you will see like fluctuations in your sales cycle. How do you tell it's a holiday? In Facebook Profit, you can go and add regressors and then have holiday calendar as a variable and plug it in. So depending on why the fluctuation is caused, you need to do your analysis on that and then try to feed that additional information as additional features into your model.
Got it. Yeah. And can you advise when to use LSTM, ARIMA, and Profit?
Start with simple. All right, and when you need a lot of explanation or something like that, think like a multivariate time series, right? Like you have because you, typically in univariate you don't want to go to LSTM. Your regular models comes into play. First is think your lot of data, Arima might not be able to handle a lot of data, so you kind of subset data. But typically in LSTM also, your context length, you're not going to give like 5 years of data. Your context length that you give, you will take last 6 days of data and predict the next 1 day of data, right? So first, the main important point I would do is, if it's multivariate time series, I will try to run a VAR model and then see like what are the features that are contributing to the outcome of the model. So when you run a VAR model, if you say like you create a VAR model with an VAR is like vector autoregressive models, you say lag as 20. It will create multiple features with 20 lags for each of the variables, and it will tell you what variables are actually contributing to it. You can get all your AIC and BIC metrics measure, and you can take that and you can build whatever model. But if you are going to LSTM, run the LSTM model with this data and try to compare the performance. In some cases where you don't need explanation, LSTM works. But if you need explanation, then where exactly gives you what features are contributing to the output. You can take those features and build one more model and then deploy it. Right? So in some cases, explanation is pretty key. Right, and in a lot of cases, your statistical models might will keep it simple and work better. Right.
Yeah. And there is another question. I was trying to decompose a time series which had a nice daily seasonality into trend, seasonal and residue, but due to high amount of abnormalities, nothing was captured by stat models. What should I do?
Nothing was captured. I kind of did not get, because something has to be captured. Maybe your residual is high. So maybe you can ping me separately how the graph looks like. If your residual is pretty high, and that's what it can capture. So that's where you need to go and maybe see like how you can reduce the residual, because your autocorrelation is not able to capture the complete trend and seasonality. So your residual is high. So this is where you get into the multivariate and add more features to see what causes the target, right? That's why it is. But this is something like I need to see. If nothing is coming out, there's some issue. You may have some missing data, and any of the stat model, if you have missing data, it's going to fail.
Got
Right.
it. Yeah.
Other than that, I cannot think at this time.
Got it. And we probably will take last two questions. How to approach real-time or near real-time models? Is the approach same as in batch predictions?
So in the real-time models, you are engineering a system that can capture real-time. Say if you have a batch model, you want to take last 10 days of data and then predict the 11th day, right? So you have everything in one place for you. You can always go and take last 10 day and predict 11 day. But take about real-time stream data. Your data is coming in, and you cannot store 10 days of data in a stream. You cannot pull from the stream, and that's where you need to think whether you need a NoSQL platform or in-memory platform that can store the 10 days of data that you can take and forecast it, right? And you have to do in streaming. So you, whatever model you are trained, you need to take that model and deploy it either as a REST API or either as an inline in-memory computing in whatever language you are using, right? So you are engineering to support that low latency requirement is very important, right? So, and how you store the data, how you access the data. And now if you want 10 days of data, and if you're just going to use an file system, you cannot look up 10 days of data from file system in a real-time flow. That's why you go for white table design and whatever narrow table design according to your need to retrieve the data. So I would say it's 80% engineering, 20% is just taking an how to deploy a model.
And this would probably be the last question. For intervention analysis, what are the approaches apart from using indicator and dummy variables?
So most of the time, you need to see like what is the process, right? Let's take coronavirus now. Now you can see a V-shaped recovery. So what happens? Everything coronavirus is done. There was downturn, and you'll suddenly see the same upturn as earlier. Or you can see like W-shaped recovery. So what is W shape? You have a downward trend. It slightly goes upper and then again comes down. That's what is happening now. We are in the second wave or third wave of coronavirus. We thought we are recovering, but we are not. And then it may go as multiple W waves before we get there. Or there's a K-shaped recovery, right? So the reason I'm talking about this is you need to understand how your recovery cycle will be in the intervention analysis. Or is there a recovery cycle, or is there new normal? Are we going to stay with coronavirus lifelong? Then you need to take that as a base and model it, right? Now, in the K-shaped recovery, some sectors will recover quickly. Like your retail will recover quickly and everything, but travel and hospitality might not recover. So that's what K-shape is, right? You have one up, which is an upward trend, the second lower, which is still lower. So you need to apply your domain and see what is your recovery cycle, or is there a recovery cycle after the intervention period. And then you need to kind of see how you can prepare your data, how you can underweight or overweight your data so that you can model it.
Great. Yeah. Thanks. Thanks a lot, Srivatsan. I think it was a very insightful session. And I think we have a lot of thanks pouring in at the same time. People were asking if you can conduct one more session on time series. But for those, I think we already have, Mr. Srivatsan has already put up a nice playlist on his YouTube channel. We can always refer, and we will also, if time permits, we can, and we'll be more than happy to have him again. And thanks a lot, sir, for your time and the insightful session. Any final thoughts that you would want to share with all the learners out there? Any general thoughts or any suggestions?
First of all, thank you for being so late in some part of the world. So definitely, like a lot of people, it's in between dinner time or their bedtime. I'm not able to see all the comments here. Once I get back to my YouTube, I will go and check the comments. But thank you very much for being here. I will. Most of the time series details are covered in my course that I mentioned. You can go and check over that. But if anything is missing, let me know. I can add that.
Great. Yeah, thanks. I think that's very nice. And thanks a lot to everyone out there for being such an amazing audience. And stay tuned. We'll come up with more interesting stuff at the same time. Please follow Mr. Srivatsan. He has some amazing stuff that is being put up on LinkedIn as well as on his own YouTube channel. Thank you.
Thank you very much.
Yeah, thanks.